Now this is our first Go program, and before I explain all the concepts, let's just run the program to see if it works as expected or not. So to run a Go program, we can do go run and the name of the file, and we can see in the console it says hello world. By the way, this character, this is in Chinese, which means world, and I will explain soon why did we write it in Chinese instead of just world in English. Okay, now first thing that we see here is a go.mod file. Now what is a go.mod file? If we look inside it, we have a couple of lines. The first value is the name of the module or the name of the project you can imagine. And the second value is the current version of the Go, or the version of the Go that the project depends on. It does not necessarily mean this is the version that you have to install in your system, but this is the version that this project, that this program depends on, this particular version of the Go. Okay, that's what it means. Now, why did we need a go.mod file in the first place? It has a couple of use cases. First thing, if you have a project, then obviously you have to name it something and you have to document the name somewhere. So that is the natural use case of a name for a project, and that we can record here in the first line of the go.mod file, the name of your project. Now, as convention, the name should be unique and it should have a prefix with your code hosting provider. And by code hosting provider, I mean it can be GitHub or GitLab or Bitbucket or anything. That is by convention, because a Go program or a Go project can be of two types. It can be of two types. Now, first type can be an executable, and the second type can be a library, or we can call it in Go's terminology a package. Now, an executable program is something that we run. For example, since we are learning about backend technologies, our programs, our Go projects will be in the category of executables, because we'll write the code and we'll run it. We'll run it in our own system, and that's how it will work. That's why it's an executable. In the same way, for people who build libraries or packages, those are the code that get imported into other people's Go projects. For example, there are a lot of packages in a standard library that we will see soon that we import into our project. For example, FMT, that we'll soon see, is a package provided by the Go standard library, which means those are the programs that those are the code that we do not have to explicitly install in our project. They are available to us by the Go runtime. Now, those are the packages that we use in our program or in our project. Now, they fall under the category of packages. In the same way, we also use a lot of external packages for building web servers, for doing validations, or for managing our configs. A lot of external packages that we will use when we are building projects, right? Those are called packages because someone has built them and they have distributed it in GitHub or other hosting providers, and we can import it into our project, which is an executable because we are running our project and we are importing the packages. So you import packages and you run executables. Those are the two major categories that you have to notice. Don't necessarily have to remember, because obviously you'll be mostly working with executables if you are building backends. That's something to remember. Okay. Now here we are building an executable. Okay. So next, after these two lines, the name of the module and the version of the Go language that the project depends on. Later on, this will also have all the dependencies of the project, all the external packages that this project depends on. That will also be recorded here in the go.mod file. So by convention, as I said, the module name should be a name of the project prefixed by the code hosting provider. So ideally, if we delete this go.mod file, let's delete this. We can generate it again using the command go mod init. By convention, this is how you name your projects. .dev.com / my username seriously / pggs. And a go.mod file is generated here, and the module name is taken from the command. So this is a conventional module name of a Go project or a Go module. Okay, that's all you have to remember about go.mod files. It has a module name, which is the name of the project prefixed by your code hosting provider. It has the Go language dependency that the project depends on, and it has external dependencies recorded here with the version numbers, so that over the time when we are adding external packages. So okay, let's just see a real world example, then I can explain better. Now if we go here, this is a project called Fider. It's an open source project for a platform. It's a feedback management platform, and it has very good Go code in my opinion. They follow a lot of conventions, a lot of idiomatic Go writing practices. That's why I often come to this repo and I study it for learning and for referencing code and different kinds of stuff. During the course of our videos, we will be following some of these good open source repositories so that I can show how these concepts work in the real world, so that you don't have any abstract idea or hypothetical ideas about how these concepts work. We'll see exactly how they work and how you will use them. And yep, so let's just see how the go.mod file looks for a real world project. So again, as I said, this is the name of the project, Fider, prefixed by the code hosting provider, which is a github.com, and this is the organization name or username, whatever is applicable. And this is the version of the Go that this project depends on, or the minimum version of the Go language that this project needs. After that, we can see these are all the external package dependencies of this project with the exact version number. So when we run this command called go space get space the package name, for example, we run go get github.com /aws/awsdk go. When we run this command, it appends that package in the go.mod file with the version number, with the latest version number, or if you specify a version number, it appends with that version number in the go.mod file, so that the next time we share our code in the hosting provider and someone else in our team, they fetch the code, they clone the repo in their local, and they can run the command go mod download, and all the packages with the exact version numbers will be fetched in their own local system, and they can use the project without explicitly doing go get this, go get this, go get this, go get this with the exact version numbers. They can just run one command and all the dependencies will be installed. So that is one advantage of using recording all the dependencies of your project in one file, a go.mod file. Those are the three major use cases of a go.mod file. It has your project name, it has the minimum Go language dependency, and it has all the external packages with the exact version numbers. That's all you have to remember. We won't have to manually change contents of this file, because we'll be mostly running commands that will make changes here. Unless we want a specific version of any package, then we can come here and make some changes in the version numbers. Otherwise, we will most likely never touch it. Okay, that's all to know about a go.mod file in a basic example and in a real world example. Now let's go back to our example. Now let's jump into the main.go file. Okay, now couple of things to notice here. We have a package declaration, we have imports, we have a function which name is main. We are using the imported package here, and we are calling this function println, and we are passing a string which gets printed in our console. Okay, that's what happening here. Now to dive deep into what exactly is happening, we have a main.go file. Okay, the first thing is the package declaration of a package called main. Packages in Go are there to organize our code in a meaningful way, in a useful way. Because what happens if you just write your code in one big file? You keep writing, you keep adding functions, and you use all the functions in the same file. It works. If it's a small program, you just want to run one script, it works. And it works quite effectively. But the moment the program starts getting bigger, you add thousands of lines, you add millions of lines, you add billions of lines. At that scale, the program will get impossible to read and it will get impossible to debug. And naturally, that's why a lot of programming languages have different techniques to organize code in a meaningful way. If we come from JavaScript, we have imports and exports, CommonJS modules and ESM modules and all these concepts. In Go, we have modules and packages. Module we already saw. If you're starting a new project, we'll run one command called go mod init with a unique project name prefixed by our code hosting provider. That's all about module. You never have to think about module in a project ever again. Assuming you're working in a typical backend based project, not on libraries. Now, second thing in the hierarchy comes packages. And that's pretty much all Go has to offer in the code management department. So packages, now the rules are every file that ends with the extension .go, it does not matter what the file name is, every Go file will start with a package declaration. It will declare which package it belongs to. Okay. Typically in a big project, a project which follows a typical Go project structure, the directory, the folder name of the folder name will often match the package name. Now, that's the first line, the package declaration. It says that this file belongs to this package called main. Now, the rule is if you are building an executable, a program that will run in your system or in a cloud or anywhere, program that will run, it is a kind of a script. It will run and it'll have outputs and logs and all. If it's an executable, it has to have one main package, and inside the main package, it will have a main function. And why is that? Because this function is the entry point of the program. And by entry point, I mean when we compile this package or when we run this package, this is where the execution will start. And the main function will call other functions and it will have different components and all. But this is where the program will start executing from. Okay, that's the rule. An executable, then it will have a package main and it will have a main function. Now, the directory structure and the file structure we'll focus on later when we are studying other projects or when we are building projects. For now, just focus on this part, the code part, not the folder structure and file. I will explain what is the ideal way to structure your files, what is the ideal way to structure your folders and all. We'll follow all the idiomatic Go recommendations. Okay, that's all about package. Package are a way to organize our code, to divide our code in different files so that it is easier to manage. Okay, and it also offers some kind of properties like encapsulation and all that we will see soon. Next line, we have a import statement which imports a package from standard library because our project name is github.com/pggs. Okay, pggs. Since we are not importing from our own module from a different package and we are not importing from an external package, this does not have any prefix or anything, which means it is coming from standard library. That's just how you can understand it, if it is coming from standard library or an external package, by looking at the prefix, the hosting provider, if it's there or not. Because all the packages from the standard library, from the Go's own standard library, is already defined in your Go runtime. You don't have to explicitly install them. You still have to import them, but you don't have to install them. So the second part is the imports. We are importing the package FMT. Now the package FMT has a lot of functions. Functions all related to print or string manipulation, everything related to strings. For now, that's all you need to know. We'll see what are the different functions provided by this package fmt. For now, we will just look at the println function. Okay, that's all about imports. Next, we have a function. Now, functions, people who are familiar with programming concepts, functions are a way to group logically related code statements or expressions, so that this function is callable and this function is grouped into one segment. Something like that. That's a typical definition of a function that we don't need to understand in a very deep way. It's just a function. And the name of the function is main. And as I said, every executable code has to have a function named main, because that is the entry point. And now inside that, we are running this line. And this is using the imported package fmt dot. And using the dot, we can access the variables, the different functions of a package that the package exposes. Okay, and here this is fmt.println, and we are passing this string hello in Chinese world, and we can see the string when we run it, when we run the program. Now another thing to focus here, this p here is in capital letter. It is not small p, and that is important. It is not case insensitive. This is definitely case sensitive, and why it is capital we'll explore soon, but that's something to notice here. Whenever you are accessing functions, variables, interfaces, structs, any data types from a package, from a different package, it always will be in capital form, the first letter. That's how we know that is exposed. Okay, otherwise you cannot access it. That is the Go's mechanism of exposing data outside of a package from inside a package. The second thing, now another thing to notice here, why did we write Chinese here? To express the concept that Go is a language which supports UTF-8, which supports UTF-8 encoding characters, which means previously in previous programming languages, they mostly supported ASCII, which is a character encoding format, which has a mechanism to express up to 127 characters, which consisted of lowercase English letters from A to Z and uppercase English letters 0 to 9, and some special characters like at and end, stuff like this. Only 127 characters, which is of course very limiting, because in our world there are like a lot of languages, and a lot of languages have a lot of different types of characters. So programming languages had to support them. So when people were designing Go, they came up with this character encoding scheme. This falls under Unicode character encoding system, which you can study more about. And UTF-8 is one encoding scheme, which almost supports, I think, around 120,000 characters from across like almost 1,000 different languages across the world, so that inside a program we can express a lot more types of characters. Okay, that's why we use Chinese here to show the fact that Go has support for a lot of characters, unlike previous languages which were only limited to ASCII characters up to 127. Okay, that's all to focus here. Now for this program, that's all the concepts. We have a package declaration, we have import statements, we have a function main, and we have used the package, and we have accessed this function from this package, and we have printed this statement, which is a string. Okay, and we can see this in the console. There is another way to run this program, to build this program. So to show one of the features of the Go, so what we can do is we do go build main.go. What it does is it generates an executable. It generates an executable, and we can run this executable using main, and here we can see the same output. What happened here is Go provides a feature which is called cross-platform single binary executables, which means a Go program can generate a executable binary, which means you can take this file, you can take this whatever main file which whose name is resembles the name of the file. You can take this executable and you can run it in any Mac operating system, the operating system that matches mine, because during the build command I did not specify which operating system or which architecture I am building the executable for. If I did mention it, then we could take this executable file and we could run it in that system. Let's say we want to generate an executable for a Windows operating system from a Mac operating system. So this is the command we can use. We can say operating system was Windows and Go architecture is AMD64 and the typical Go build. We can mention the file or we can just say dot and it will take the file by default. If we do this, then it will generate a file called pggs.exe, and if you are aware of it, .exe is the Windows executable file extension. So now you can develop your backend in your system, which is a Mac operating system. And now you can compile that code using Go build, and you can compile that code for a Linux operating system or a Windows operating system. And now you can send these binaries. Now you can send these binaries to other system and they can just directly run it and they will have the same results without installing Go explicitly. Because when we generate an executable, all the Go runtime, whatever dependencies that are needed by the program, that gets embedded into that single binary executable, and that gets distributed across different systems. So this is a huge advantage that Go offers, that you can run a single command and you can generate different executable for different operating systems from any operating system. Okay, now let's delete these. Now another question to ask here is, what is the difference between the command Go run and Go build and running that executable? So the one line answer to that is, while you are developing, you should use the Go run command. And what Go run command does is, Go build, it goes through your code, it compiles all the packages and it does all the linking and all, and in the end it generates the binary. But Go run command does is, it goes to the code and it compiles all the package and it directly runs your system without generating a single binary. It directly runs your program with a temporary binary somewhere in the system. And it is relatively faster because a Go build command, after compiling all the packages and linking and stuff, it throws out all the results of the compilation into the garbage. No? It does not store anything. It does not cache anything. So the next time you run Go build, it again starts from scratch. That's why it's a little slower process. Now Go run, what it does is, after compiling and after linking, it saves that result somewhere in your system. And the next time you run Go run, if nothing has changed in those files, the results will be faster, and it will use those cached results to compile your program faster and to run your program in faster. So that is one advantage of Go run. When you're building in your local, when you're developing your application, you will typically use Go run instead of Go build, which you will usually use when you're deploying your application, you're distributing your application across different systems in your CI/CD pipelines or in cloud development environments. Typically, we use Go run command to run the project, to run the program in our local. Okay. Now moving on to the second example, we have one little change here. We are using another package called math.rnd, and this is a package which we can use to generate random numbers and typical functionalities like that. And again, we are using the same println function from the package fmt, and we are printing a random number between 1 to 10. Okay. And if we run this program, Go run Go, we get a number 9. And if you run this again, we get 3. If you run this again, we get 3. Again, it's 0. So basically, every time we run the program, we'll get a random number between 0 to 10. Yeah, that's just a basic example. Now, another thing to focus here, the reason we are looking at this example is this part. When some packages, most packages will have these prefixes, the path the package can be accessible from. But those are not the important parts. The important part is the last part after the slash. So that will be the name using which you will use that in your own program. So because the last part was RAND here, that's how you referred it, rand.intent. Now, because of how we access the packages using the name of the packages throughout our systems, the convention, the standard practice, the best practice to name your packages, first thing, the package name cannot be capital letter. It has to be small case, like we have here, the main package and the FMT package and the RAND package. All the package names have to be small case. The second thing, the package names have to be as short as possible. Now that is not a rule, but it is a convention, because since when you import a package, it can be an external package or it can be an internal package from your own project. You will use that package using that name throughout the execution of your program. So you don't want to write a 10 letters package name again and again and refer it by that name, because that will be very cumbersome. That's why it is advised that your package names should be as short as possible and all small case. Okay, we can take a look at how people name their packages in a real world example. So if we go to our FIDER project, now we can open any projects. Now again, don't focus on the folder structure and all the code, just look at the package names. Here you can see the package name is actions. The package name is action tests, is actions. Now, as I said, typically the package name matches the name of the folder. Now, as you see, there is a folder named actions, and all the files inside that will have the package actions. Apart from the test ones, we have not gotten into tests yet, but this is how people name their test packages using _test. So all the files in this folder will have the same package actions. And as you can see, it's small case and it is pretty short. Similarly, if you go to handlers, we'll see handlers, all the files inside the handlers folder will have the package name handlers, any file you go. And it is also pretty short and it's in small case. Same way, if you go to webhook folder, the package name is webhooks, it matches the directory name and it is a pretty short name. So that's what I wanted to show. In real projects also, when you see the package names are all short. As you can see, this is how people import the packages. If they have multiple packages, instead of writing import crypto RSA, import crypto RSA, sh1, this is a format we typically follow when there are more imports in a Go file. So we write an import and there is a starting braces and there is an ending braces, and all the package names are written in different lines. And as you can see, the last part, the IDE here, VS Code, it highlights the package names here, and it makes it easy to understand. But even if you're working in IDE which does not do this, then also you can refer to that package using the last part, the last component. All the package and the conventions that I was mentioning, the package names are short and they are in small case. Okay, that's all you have to remember. They are packages and they have to be named in small case. The name has to be short and they have to match the folder names. We have not gotten into folders yet, but that's something to remember that we'll use in the future. Often packages reside in a folder which matches the package name. Okay, great. Now going back to our own example, that's all here to notice. Okay, now let's go to now in this example, we are importing the package math from the standard library and we are trying to access a variable named pi from the package math. The rest of the things are pretty much the same. We have the package declaration main, we have the import statements, we have the function main, we are printing something. Okay, the structure is pretty much the same. Now we are doing something new here. We are trying to access a package name. We are trying to access a variable from a package math. Now if we hover, as you can see, there is an error here, and if we hover over it, it says undefined math.py. But we know that there is a variable named pi inside math package. And what happens if we try to run this? And you can get the same error, undefined math.py. Because we are using VS Code and it has support for the Go language, it has the LSP integration, we directly get compile time errors in the IDE itself. We don't have to run it explicitly to get these errors. So that's one advantage of using a IDE which has first class support for the Go language using the extension. Now, the thing to focus here is, as I mentioned earlier, whenever we are accessing a variable, a function, an interface, a struct, an array, whatever the data type is from a package, from inside another package. So we are in the main package right now, and we are importing the standard library package math, and we are trying to use a variable called pi from the math package. In this scenario, when we are in a different package and we are trying to access something from another package, the name will always have to start in capital letter, because all the variables, all the data types that start in small case, those whose names start in small case, they are hidden from external access. Only those data types whose names start with a capital case are accessible from outside the package. So this is one example of Go's encapsulation technique. So if you come from a programming background and typically object-oriented programming, you're familiar with the concept encapsulation. It is a technique to hide the implementation or private variables and stuff. So Go offers something like that. You should not think in terms of object-oriented programming when you're coding with Go. But if you want to relate, you can think of this as encapsulation. So for this to work, we have to make this capital case. We make this capital case. And now if you hover over it, there is a variable, there is a constant named pi, and it is a float type. We will explore data types soon. And now if we compile it, we can see the result here. It prints successfully because we are now accessing it using a capital case letter instead of the small case, because a package data types are only accessible outside of the package using capital letter. Okay, that's something to remember. In this example, we are looking at custom functions. The main is also a function, but there will be thousands and millions of other functions in a typical life cycle of a program. Now we are looking at one of those functions, how to define functions in Go. Now this is the structure a function follows. First, we have the keyword func. That's how a function starts. Then we have the name of the function, whatever name. Typically, we give a function, the name of the function. Then we have a braces inside which we'll have parameters, and the parameters will follow the structure, the name of the parameter and the type, comma, the name and the type. Okay, that's the structure we'll follow for parameters. Then we will explicitly have to define the return type of the function. It is mandatory to define what type the function will return. Now we'll explore data type soon, so nothing to worry. Just focus on the function part here. We'll define the return type here. Then we'll start a curly braces in the same line. Then we'll write all the statements here, and we'll end the curly braces. This is how the typical structure of a function looks like. And now we can call the function inside println, and we can provide two arguments of type integer, because we have defined it is an integer type, because Go is a statically typed language, which means all the types are verified and they are checked during compile time. So now if we try to provide a string here, and if you hover, it says cannot use h untype string constant as an integer value in the argument to add. So it is, since it is a statically typed language, Go is a statically typed language, we can only use the defined data types that a function accepts. We cannot use random any data types. See, it has to be an integer. Okay. Now, if we run this, we get the result 49. 42 plus 7, 49. And that's pretty much all you need to know about functions, how to define functions. So this is the structure you have to remember. It will have a func keyword. the name of the function, then the parameters inside the braces. The parameters will follow the structure of name, then type, name, then type. Then it will have a return type, and inside it all the statements. Now we can modify this function a little bit because both of the parameters are of type integer. Now what we can do is we can write x comma y integer. Now this is also an acceptable form of writing function parameters, but in my opinion, I prefer the earlier type because it, on the first look, it explicitly says x is of type integer and y is of type integer. Now it is a little easier to our eyes. It is more readable and less likely someone will misunderstand by looking at this. Just my preference, but of course you can write the other way also. If both the parameters are of the same type, then you can get rid of the type of the first parameter and add it to the end of second parameter. Okay, that's all about the structure of the function. Go has a feature that a function can return multiple values from inside it. And to demonstrate that, here we have a function called swap. It takes two parameters and it's in the merged form where both the parameters are of type string. So we have removed the string type from after x2. We have merged it here after y. Okay, it takes two parameters, x and y. Both of them are of type string, and it returns two values. And when we return more than one value, we have to add braces here. Okay, if it's a single value, we can write just string without the braces. If it's more than one value, we have to write braces here. It returns two values, both are of string. And what it basically does, since we are swapping, it takes x and y and it returns y and x. Okay, and we can use the swap function here, and we provide it two arguments. One is hello and second is world in this sequence. And we can take the values returned from this function. So it returns two values. Now we can use this structure, the comma separated variable structure, to read both the values returned by the swap function into these new variables. Now we'll get to what's happening here soon. But for now, let's just focus on the multiple return values. A function can return multiple values, and to read that, we can use this structure, a comma separated list of new variables, and both the values will be read into these variables in that sequence. So y will be inside A and x will be inside B. Now world will be inside A and hello will be inside B. And if we try to print it, when we run this program, we'll get world hello instead of hello world. Okay. Now, the only thing to focus here is Go has the capability to return multiple values from a function. Okay. Now there is another way to define your return values in a function. So we have a function split here, which takes one parameter of type integer, and the parameter name is sum, and it returns two values of type integer. But instead of writing it like this, int comma int, we have written it like this. What we have done is we have named those return values with x and y. And with this structure, what happens is when we name our return values, those two variables are initialized. They are initialized with their zero values. Since it is an integer type, now with the start of the function, before anything is executed, before the first line, two variables are implicitly declared. Now we have x equal to 0, y equal to 0. Now, because of that, if you see here, we are not initializing a variable anymore. We are directly assigning it. We'll get to the variables right after this, but for now, let's focus on the return values part. Both the values are implicitly initialized, and now we are assigning values to those two variables, x and y. Okay, we are assigning this. And now because of that, we now don't have to write return x comma y. We don't have to write like that. We can just write return, and what the program will do is it will return x comma y in this format from the program body, whatever the x and y's values are. And if we try to run this program, we are getting 7 and 10 after the calculations. Now, this is something Go supports out of the box, but my suggestion is you should not use this format. I have never used it. I don't want to use it because it is very difficult to track. So let's say it's a very large function and you are at the end of the function, and now you look at this return. Okay, and now you want to understand what this function returns. Now you go to the first part of the function, you look at the x and y, and now you try to find those variables in the function body. Now you have to track a lot of stuff to understand the flow of the program. Right? It just makes things more complicated than they have to be. So for that reason, I prefer to use the explicit return type. So in this case, what should ideally happen is we should just do int, and we should initialize these variables like this. We'll get to the initialization variable part right after this. Now I should give x comma y. Now if we run this program, we're again getting 7, 10. Now if you read this, this is much more readable. We are initializing 2 variables and we are returning x comma y. Okay. The implicit return feature is not very readable and it is prone to mistakes. So you should know that they exist, but you should not really use them unless you would want to. Then feel free to. Now let's understand about variables. Okay. Now this is how we declare variables in Go. Outside of the function, we can write the keyword var and the name of the variables. And if all of them are of the same type, we can just add the type at the end. If they are not of the same type, we have to add the type after each variable's name. Since all of these are of the same type, we can just write bool at the end, and all these variables are initialized to their zero values, because in Go, a variable is never in an uninitialized state. It is never in an undefined state or null state. A variable, a struct or whatever the data type is, always initialized to its zero state. So since it is a of type bool, it will be initialized to its zero state, and the zero state of boolean is false. Okay, this is how we declare variables outside of a function body, inside a package. This is not inside any function, because that's why this is the only way to declare variables outside of a function. Now if we are inside a function, we have a couple of ways to declare a variable. The first type is this, the same way we define the variables outside the function using var, the name of the variable and the type of the variable. And this will initialize I to the zero value of integer. What is the zero value of integer? It is 0. Okay. And if we try to print these variables, let's just run it. We get 0, false, false, false. The 0 for I, and since C, Python, Java are all initialized to the zero value of boolean, they are all false. Now there is another way to declare and initialize variables in the same statement. That is only doable inside a function. We cannot do it outside the function. So we can write it here, I with colon equals to 0. And if we follow this pattern, it is pretty short to write, and this is one of the patterns that you'll use mostly. You'll also use the var pattern, but if you already know the initialization value of a variable, then you'll use this pattern, the colon equals to. And since we know the i's value has to be 7, now we can do this. And if we print now, and print 7 false, false, false. Now this format, this colon equals to format, is only accessible inside a function. We cannot do it outside the function. If you try to do it here, let's do it. Let's do k colon equals to 8. If you hover over it, it will say expected declaration found k. So all the declarations outside a function has to follow the var pattern. It cannot follow the colon equals to pattern. Okay. Now there is another way to write it using the var pattern. You can say var I equals to 10, and if you print it, it prints 10. And using the initializer, it interprets that I is of type integer. Okay. And this is just a long way of writing the colon equals format, because this is the same thing as writing if we take out var and we just put colon here. So this colon equals to is kind of a syntactic sugar, a short way of writing this var. Okay. If you don't want Go to interpret the type, we can write var I, can write string. Now the moment we write the type here, the initializer value has to support this type. Now it says cannot use 10 untyped integer constant as string value. Now we have to make this a string. Now it satisfies. Print it. It prints 10. Okay. Those are all the ways you can initialize variables in a typical Go program. Now, if you have questions now that which pattern to follow when, this is how you should think about it. These are the rules. First rule is if the initial value does not matter and you're fine with it initializing with a 0 value, then go with this pattern, this var I integer. Since it does not matter what the initial value of I is, and we will set the value of I in the course of the program in a later phase, we can initialize it like this. It implies that to the reader of the program, whoever is looking at the program, they now can understand your intention that variable I has a value of 0 when it is initialized, and the initial value of I does not matter, and the value of I is set somewhere later in the execution of the program. So that's the first type. The second type is if you know the initial value of the variable and it is important, then you can go with this colon equals to. Now, since you know the initial value of the variable I is 0 and it has to be 0 and it is important for it to be 0, then go with this pattern. Okay. The third thing, if you are outside a function like this, if you are outside a function, then you don't really have a choice. You have to follow this pattern, var c bool. You can also initialize it here, var c true. Okay, those are typically the 3 patterns when it comes to variables that we have available in the language. Now, to get a little concrete idea about how people use variables in a real system, let's go back to our example of Fider. A couple of examples that we can see using the var form of variable declaration is here. As you can see, these variable declarations are outside of a function. They are in the level of package. They're the package level variables, and that is the reason they have declared it using var, even though they knew the initial value. And in the same way, these variables are declared in the package level, and that's why they are declared using var. And you can find a lot of examples like that. All the variables that are declared at the package level, they have to be declared using var. And another example, which is declared inside a function and still uses this pattern of var instead of the short declaration of colon equals to, because they have initialized the variable at this stage, but at this stage the initializing value does not matter. The value that will be assigned to this variable, which is of type error. It is of type error, but the initial value does not matter. We don't have an initial error value. The value will be assigned during the execution of the program. So if you focus here, the value is actually assigned to the ERR variable is at this point. At this point, this function returns an error type in the second return value, and that's what gets assigned to this variable. Okay. So in this pattern, when we have a variable that for which the initial value does not matter, in that case, we can go with this pattern. In the same way, if we look for the colon equals to pattern, let's look for the colon equals to, do a global search, and you can find this pattern pretty much everywhere, because most of the time most of the times we know the initial value of our variables or of our data types. So in that case, we pretty much go with this pattern. For loops, we have not explored for loops yet, but there also we use this colon equals to, the short declaration form of variable declaration. You can find this example everywhere. This is the go-to method of initializing variables when we know the initial value. Okay, so those are the 2 things that you have to keep in mind. Eventually, when we do more practice, when we use variables a lot in Go, you'll get it. You'll get which pattern that we use where. For now, just know that these two kinds of patterns exist in a typical Go project. Moving on to the next example, which is of data types. So in this example, various data types are declared. We have Boolean, we have an unsigned integer, we have a complex, and we are printing the variables and the type here using printf. Okay, and we are using the %t verb. %t verb is used to print the type of a variable, and %v verb is used to print the value of a variable. There are other verbs, which is %s to print the value of a string. There is %q to print the value of a string in double quotes or single quotes. Okay, and there are different verbs that you don't really have to remember. The more you use, the more you will get the idea, and you'll remember the pattern the next time you need them. So let's see. So what are the data types that we have on a high level? All in all, let's say Go has 4 major types of data types. The first one is basic. In basic, we have number, we have string, and we have Boolean. These are the 3 major categories inside the category basic data type. The second data type that we have is aggregate data types, and these are of types array and struct. Array is basically a collection of similar data types, collection of homogeneous data types. You cannot store a string and a number inside the same array. The type has to be same for all the values inside an array. And inside a struct, in the opposite way, struct is a collection of heterogeneous data types or different kinds of data types. You can store an integer, you can store a string, you can store a boolean, all inside the same struct. So that's the difference between array and struct, and they are called aggregate data types because they consist of different basic data types inside them. Okay. We have the third type, which are called reference data types. Reference types, inside them we have pointers, which we'll explore soon. We have slices, we have functions, we have channels, and we have maps. These are the 5 reference data types, and they are called reference data types because they themselves don't contain the data as a container. They refer to some data type which works in the background, and they refer to that data for functioning. That's why they are called reference data types. They don't have the data in them. They refer another data type to access the data. And we have the fourth one, interface types. We'll explore interfaces later, but they are another major type in Go. So these are the 4 major categories of data types in Go. And inside basic, we have number, string, and boolean. So if you go here in the tour of Go, here we can see we have boolean, we have string, and we have inside number, we have all these categories. We have integer, we have integer 8 and all these numbers 8, 16, 32, 64, and uint, which stands for unsigned integer, and 8, 16, 32, 64, etc. So what is the difference? What do these numbers mean? These numbers basically help you to decide the size of your variable, to decide the size of your variable. How? Let's imagine int 8. We take integer int 8. What this means is this variable can have numbers between -127 to 128. And how did I derive this range from this number 8? So this 8 means basically this variable can use 8 bits to represent the number. So 8 bits means 2 to the power 8, which is roughly 256. And 256, since it is a signed integer, we can have negative numbers inside this. If we divide this, this range can be -127 to +128. That is the range. We can store numbers inside this range in int 8. And in the same way, you can derive what can be the range for int 16 or int 32, etc. And for uint, the unsigned integer 8, what that means is, since it is unsigned, we can only have positive values. So 2 to the power 8 which means 256. So our range can consist of 0 to 255. We can assign numbers inside this range. That's what these numbers mean. What can be the range of your integers? How much size that you want the language to assign for these variables. Now we have other two types, which are integer and uint, unsigned integer. What these mean, for example, if your operating system is of 32-bit architecture, then int will have int 32 in size. And if your architecture is 64-bit architecture, then int will have int 64. Same for uint 32 and uint 64. So the Go official documentation recommend that you should always go with integer and unsigned integer, depending on you whether you need positive values or negative values. You should always go with the system defined variable units. But there are times when using int 8 makes more sense than using int, which if you have a 64-bit architecture, which will have int 64. In cases when you exactly know what is going to be the range of your integer value. For example, if you take a look at finder and we try to find uint 8, and if you take a look at here, we don't need to understand what's exactly happening in this system, but all in all, on a very high level, we can understand this, that there is a type which has the data type uint 8, and we are declaring some variables of different levels. And on a very high level, without understanding anything, we can say that they need this level type to be the range from debug 1, 2, 3, 4. So maximum 1 to 5. This range is enough for this use case to define different levels of logs inside a backend system. Okay. So in this case, if they had gone with the system defined unit, which is int or uint, then that would have assigned the uint 64 unit, and that range is a little bit too much for this use case. So 2 to the power 64 can have these many numbers, which they don't need for this use case. So for this, they went with the smallest available unit for unsigned integers, which means unsigned integers 0 to 255. So since they know their range is going to be maximum 5, or in the worst case 10 or 12, if they come up with more levels in their logging. So worst to worst case 50. You want to go ridiculous levels. It cannot exceed more than that. So for this use case, going with a uint 8 saves a lot of memory for your system. So it's pretty much common sense that if you beforehand know the range of your integer, if you know what is the maximum value you can assign to your integer, go with that range. So that's the mental model you can use to either go with any of the numbers, any of the weighted units. Now, while working on backend systems, when dealing with user data or data that you are not very sure of what is going to be the size of those integers, then you can safely use integer. It is not a very huge performance effect, since Go official documents also recommends you to use the system defined unit. Okay, that's the mental model you should have. Then we have byte, which is an alias for uint 8. Bytes are also used to represent strings inside Go. We'll explore more on that later. Then we have rune, which is an alias for int 32, and it is used to represent UTF-8 characters inside a Go program. Then inside float, we don't have system defined units. We only have float 32 and we have float 64 to define different floating point values which have decimal points, 32.64, something like that. Okay, those values can be used using float 32 and float 64 data types. Then we have complex, which I have personally never used, but you should know that they exist. Okay, those are all the data types. Those are all the different data types inside basic. These are all the basic data types that we have available in a Go program. So going back to our earlier example, this is a program which defines a Boolean unsigned integer 64, a complex data type, then we are printing the type and the value. And if you run this, then we can see the type bool even 64, complex 128, and the values of the variables. That's pretty much all there is to it in basic data types. We have integer, we have numbers, we have strings, we have booleans inside numbers, we have signed integers, we have unsigned integers, we have floats, and we have complex and bytes and runes. Great. Another concept that we can touch up at this point is, which I have already mentioned, that Go always initializes variables with their zero value. And by zero value, I mean for integers. For any number data types, the zero value is 0. For any booleans, the zero value is false. And for any strings, the zero value is an empty string, a empty quote. Okay, those are all the 3 basic data types, and those are all the zero values that you have to remember. There is another zero value called nil, which we will see when we look at reference types. All the reference types will have zero value of nil. Okay, and we are printing here using %v. %v prints the value in Go format of any variable, and here we are using %q. %q is basically printing a string with quotes. Okay, and if we run this program, we can see 0, 0, false, and empty string. So in this case, if we change this from %q to %v, then what happens? We don't see the quotes anymore. So if we want to print the quotes, then we have to use %q. That's the use of %q verb. So in case of strings, it will explicitly print the quotations. Okay. Next up, we have type conversion. Type conversion basically applies in statically typed languages like Go, because unlike dynamic languages like JavaScript or Python, conversions are not done implicitly by the language. You cannot assign a float value to an integer value, and you cannot depend on the language to implicitly convert it. You have to explicitly convert the value. That's all there is to it. To understand that in Go, every data type needs to be explicitly converted into another data type. There is no implicit conversion, even though a number satisfies. So in this case, let's say you have an int 64 value and you have an int 32 value. Even though both are the same numbers, let's say both have the value 32, and this variable is k, this variable is v. Even though you have this use case, you cannot assign the value of k to the value of v, because the internal data type is int 64. Even though the values are same, they are both the integers and they both satisfy each other, you still have to explicitly convert like this int 64, the name of the type, and pass the value of k. Then you can assign it to v. This is the format that you always have to follow. It does not matter whether the type internally satisfies us or not. You have to explicitly convert the types before assigning. Okay, so in this example, what's happening is we are defining two integers, x and y, and we are calculating a value of type float using these two integers. And we are trying to assign the value of that float to another unsigned integer using explicit type conversion here. So if you try to remove this, if you try to remove the explicit type conversion, then we'll get this error. If you hover over it, you will see cannot use f variable of type float64 to unsigned integer. And if you try to run this, we'll get a compile time error for the same. Now, that's pretty much all there is to it. Every time you want to convert one type to another, you have to do explicit type conversion. You cannot depend on implicit type conversion. And usually you don't have to worry about this while you're developing applications. You will get these errors while you're developing in your IDE itself. You won't get it during runtime because these are compile time errors and your IDE can catch it using LSPs. So you will get these errors and you can fix this. So you don't have to actively worry about it. You will get hints from your compiler to fix your errors. So we can go back to it, and using the explicit conversion, we can print the value 345. Next up, we have type inference. What type inference means? When we are using a short declaration form using colon equals. In this form, we don't define the type of the variable explicitly. We let the language go, the Go runtime the compiler to derive the type using this initializer value. So in this case, if we hover over it, we can see that the type of value is integer because we have assigned 42. So if we change this to 42.7, and if you see this, now this is a float 64 value. And in the same way, if you change this to a string, and if we check this, this is a string. And another thing to notice here is, once the type inference infers the type of the variable with the initializer statement, in the later phase, if you try to do v equals to 9, in this case, you will get the error that cannot use 9 untyped in constant, integer constant as a string value. So once the compiler infers the type from the initialize statement, you cannot change the type during the course of your program. The type will be constant. The type is only inferred once and it stays like that throughout the execution of your program. That's why Go is called a statically typed language. Okay. Next up, we have constants. We declare constants using the keyword const and we assign a value. You always have to initialize a constant. Otherwise, it's an error. So constant have some properties. First thing is they are, of course, constants. And what that means is you cannot change the value of a constant in a later phase of a program. The second thing is they are they are evaluated during compile time. And that's the reason we always have to assign some initializer value to a constant, because the values of constants are evaluated during compile time. They are not evaluated during runtime or when the program is executing. During the compilation phase only, the program will know the value of the constants. So if you try to run this, we get all these values printed. And what if we try to change this? Truth equals to false. And if we hover over it, we'll get that cannot assign to truth because it is a constant. And if we try to run this, we'll get a compile time error that cannot assign to truth because it is a constant. So what is the difference? When do we use variables and when do we use constants? What is the mental model there? So basically, every time that you have some hard-coded value, you have some predefined value, whether it is a string or a number or a boolean, because constants can only have these three data types in them. A constant can be a boolean, a constant can be a string, or a constant can be a number. These are the only three data types constants are allowed to have. So when you're developing, if you have a use case where you have a hard-coded value, you have a port that you want to listen to, or you have a URL that you want to make a request to, or you have an allowed set of values that you want to validate against, any kind of hard-coded value. So instead of using the hard-coded value as it is, you can name the value using a constant. And that implies that this value does not change ever during the course of your program execution. And it has a semantic meaning and it also has a runtime meaning because constant cannot change. So if we look at the use of constants in our example, of a real world example, we can do a search here, const space. And if you try to go files, so as you can see, it's kind of implementing an enum pattern using Go, using constants. So it has an allowed set of values. We will see what are enums and how to implement enum pattern in Go later on when we are building projects. But as of now, you can see that these are some hard-coded values. And in order to name them in a meaningful way, we are using constants. In the same way, we are using 1, 2, 3 hard-coded numbers to a meaningful name, that a role visitor, role collaborator, role administrator. Okay. In the same way, there are hard-coded values here. There are hard-coded values here. So that is the pattern. You have a hard-coded value. You want to name them. You want to name them in a meaningful way. Those are the scenarios when we use constants. Next up, we have